Okay, so we found how to perform the split. So in this fashion, the system has evaluated all the possible 19 splits, and of all the 19 splits, it found that splitting at income of 94,950 is the best one. Okay, that is, this split results in two sets which are most homogeneous as far as is possible with the given data. Okay, and if we calculate the deviance for this set, it is 46,321. That is, you take all these values and calculate the deviance, and you take all these values and calculate the deviance, it is 79,567, and you get a total deviance of 125,888, which is just the sum of these two. Okay, so the first split resulted in reducing the deviance from 478,514 to 125,888. Okay, and there's no split that will help us to do better than this. Right, the system actually evaluated all possible splits and arrived at this. Okay, so now once again, what are the possible splits? Well, we now have two data sets, right? You've got the left-hand side, which is this, that is all the cases for which income is less than or equal to 94,950. Those are these cases. And on the right, you have these cases for which income is greater than 94,950. You've got these. Okay. Now, on this set, you have a certain set of splits possible, right? So you again sort all the incomes, and then you see which are all the possible places at which income can be split. And here again, family size, which are the possible places at which family size. So a certain number of splits are possible on this, certain number of splits are possible on this. And of course, each one of those splits, if you perform, will provide a certain amount of deviance as a result, the total deviance. Okay, so what we want to do at this point is to evaluate all possible splits on this, and perform that split which reduces the deviance the most. Okay, I'm not going to obviously repeat all of those calculations, but the system does that, and the system finds that this is the best split, right? Splitting at family size equals 2.5. So here are all the cases where family size is less than 2.5 and income is less than 94,950. And here are all the cases on top for which family size is greater than 2.5 and income is less than 94,950. And here, of course, are the cases where the income is greater than 94,950. Right? So now we have three nodes. Right? You have three leaf nodes. So this is on the outside is the overall data set. That's the root node. These two nodes, that is this left-hand side and this right-hand side, resulted from the split on the root node, and these two nodes resulted from the split on the left-hand side node. Okay, now let's calculate the deviance. Of course, this deviance remains unchanged, 46,321, because we didn't split this thing, right? But this one we did split, so we now have a deviance of 16,071 for the top part and a deviance of 17,400 for the bottom part. Okay, now all of these are calculations. If you like, you could go and actually verify them with R. Okay, so the deviance reduction, earlier we had a deviance of 125,888. Now the resulting deviance is now the sum of all these three, which is 46,321 plus 16,007, 17,400, and that is 79,792. So again, we got a deviance reduction from 125,888 to 79,792. And once again, among all the possible splits that were possible on this right-hand side and on the left-hand side, this is the one that yields the best deviance reduction, maximum heterogeneity. Okay, so and in this fashion we continue, right? So the next split the system suggests should be here. Okay, and income at 113,500. And once again, if you calculate all the deviances, you get these. And you see that the deviance now reduced from 79 to 53, which is just the sum of all of these. Okay. Again, at this point, once again, there are several splits possible on this, several splits possible on this, several on this, several on this, right? The system is going to consider each one of those splits and add up all the resulting deviances and choose the one that is the best. And it turns out it finds the best one is that one. Okay, to split at 3.5 on family size. Okay, so now if you do the resultant, this deviance incidentally is 0 because both the values are exactly the same, 600. Okay, and now if you add up the deviance, you see that it goes down from 53 to 41,887. Okay, and next split, the system suggests again takes this rectangle and splits it here, and it gets a deviance of 27,187. Okay, so that's the process by which splitting goes on. Of course, and splitting can continue. It can keep on going on further and further and further. Of course, it will be stopped when there is no more split possible. For example, here there's no split possible. Or you might consider get into a situation where you've got a node that has only a single case. Again, no split is possible, right? So it could be that, or it would stop splitting when you've got a condition like min bucket or min split, right? So if you put those conditions, then again, if you say, well, don't split a node if it has less than 10 cases, min bucket equals 10, right? Then it will stop at that point. It won't split that node any further, even though splits are possible. Or alternately, if you say min split is something, that is, don't create any node which has less than that many cases, then again it's going to do the same thing. Okay. Of course, the kind of branching depends upon attribute type. So for example, if you've got numeric, then of course the branching is based on less than equal to and greater than. So for example, height less than equal to 25, salary less than 35,000, etc. Whereas if you have categorical attributes, the splits are based on equality, right? So you've got color equals red or green, right? It's going to, the equality will be the condition for yes, and not matching is the condition for no. Okay, there's one other case when you have categorical but ordinal, right? If it's ordinal, then splitting works exactly like numeric. If it's ordinal, then tree basically treats it as numeric, and splitting will work just like this.